Here we go with more conservation of energy. So in this lesson, there isn't anything really new. We're just going to keep practicing the concepts that we learned from the last lesson. And remember that the main idea from that lesson was that energy is not created or destroyed. It only changes forms. So we always started out with this equation which says the potential energy initial plus the kinetic energy initial is equal to the potential energy final plus the kinetic energy final plus, if there is any energy lost to heat, turned into heat, usually due to friction. So it's this idea that we're going to be pounding this lesson with lots more examples, and then it'll be your turn to practice. So example number 1. A slingshot is pulled with an average force of 70 newtons for a distance of 90 centimeters. So distance, it's pulled back to stretch the elastic with the force of 90 newtons. How much potential energy is stored in the slingshot? So this isn't conservation of energy yet. This is just reminding you that the work done on the slingshot is the same as the potential energy stored in the slingshot. So we know that work is force times distance. We need these to be in base units. So 70 newtons, that's fine. 90 centimeters, you need to convert from centimeters, 100 centimeters in 1 meter. This is going to get us 0.9 meters, and that's the number we're going to plug into our formula, so base units. So force of 70 newtons times 0.9 meters. Pull out your calculator for that one, or if you know, 7 times 9 is 63. So this is actually going to be 70 times 0.9 is the same as 7 times 9 is 63 joules. So the potential energy, which is the same as the work, is what's stored in the slingshot is 63 joules. Now, if there is a 35-gram mass in the pouch, how fast will it leave the slingshot? Now we are dealing with this equation right here, assuming that there is nothing lost to friction. So let's put that down here. So we have potential energy initial plus kinetic energy initial is potential energy final plus kinetic energy final, and we can start eliminating things based on what we know. So potential energy we know is this potential energy initial that we calculated in part A. Since it's not moving before you let it go, we're going to eliminate this kinetic energy initial. We're holding it still, it's not moving. Potential energy final, well, we're thinking we're going to let it go. So all of that work that we put in is no longer going to be there anymore. We can eliminate that term. And kinetic energy final is what happens because it's moving. So we are going to have this term. So this is my 63 joules. So I'm just going to leave this as PEI for now. Is the 63 joules from up here. And this is my 1/2 mV final squared. And we are looking for what is V final. So multiply both sides by 2 to move the half to the other side. So times 2 to cancel the 1/2. Divide out the m to move that to the other side. Divide out the m. So those cancel. And then we're going to square root to get rid of the squared. So my equation becomes VF equals square root of 2 PEI over m. And then we just start plugging in my information. So 2 PEI is the 63 that I calculated, and the mass, again, this 35 grams I need to convert to kilograms. It's essentially going to be divided by 1,000, so this is 0.035. And at this point, we need to pull out our calculator to plug in our numbers. And when I do that, lo and behold, I get an exact velocity of 60 meters per second. You might also almost think somebody planned that. To get 2 or 3 sig figs, 2 sig figs, I put a decimal in. To get 3, I'd put 0.0, and that would be my final answer, 60 meters per second. So even though this energy was pretty low that we stored, because it's such a small mass, it actually ends up going pretty darn fast. So next part, example number 2, Tarzan. Tarzan weighs 82 kilograms and can run at 8 meters per second. He runs along the ground and grabs a vine, swinging into the air. What maximum height does he reach? This DALP stands for draw a little picture. What in the world is going on? So Tarzan is running along the ground. So here's my ground, here's my Tarzan running. Maybe you can draw a better picture of somebody running. And he is running at 8 meters per second. Runs along, and he's going to grab onto this vine that's hanging right there in the air and swing up into the air until he comes to a stop. Maximum height, he's going to stop. So V final in this case is going to be 0. Hopefully you remember that maximum height from kinematics from last year. So he's running along the ground, swings up into the air, and we want to know, what is this height above the ground? How high does he get? So again, we're going to start out with this equation: potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. We start with this every single time, and then we try to think about how we can eliminate terms to make this a little easier on ourselves. So since he's running along the ground at the beginning, he's at ground level, I'm going to eliminate this PEI and say his height at the beginning is going to be 0. He is running at the beginning though, so KEI not going to be 0. I'm going to make this 1/2 mvi squared, and that's what this 8 meters per second is my VI. That is equal to, well, potential energy final. He definitely ends up with a height at the end. That's what I'm looking for. So this is mgh final. And when he cuts to his maximum height, he's going to come to a stop. So we're going to eliminate this kinetic energy final because his V final is 0. And at this point, this leaves me solving for it, my H final, which is going to mean dividing out the mass and dividing out G. And when I do that, my masses are going to cancel. So it doesn't even matter that he's 82 kilograms. What really matters is how fast he's going at the beginning. So my equation for H final becomes 1/2 V initial squared over G, or you could also write this as V initial squared over 2G, either way. Plug in your information. So V initial is my 8 squared, 2, and G is my 9.8 that I always have. So my H final, if I pull out my calculator, is 8 squared divided by 2 times 9.8. Make sure you have those parentheses on the bottom, or it's only going to divide by the 2 and just multiply by 9.8. And this tells me the final height that he gets to is 3.265, so 3.27 meters high. So again, we always start out with the same equation, but a lot of the time we can eliminate information based on what we know. So this PEI was eliminated based on the HI is 0, and this KEF was eliminated based on the fact that V final is 0. Anywhere we've got zeros going on, we can delete things and make our lives just that little bit simpler. Slap shots are a great example of energy transformation. These are in hockey, so you're gonna see in the video coming up a slap shots in slow motion. Watch for the transformation of energy from kinetic energy as it moves at the beginning to potential energy as it goes up into the air.
Hey, it's me, Destin. Welcome back to Smarter Every Day. So it might surprise you to know that we have hockey at the university that I went to. Anyway, today we're going to talk about the physics of a slap shot to get smarter every day. No way, you're missing a tooth? That's so stereotypical hockey player. Can I see it? When did you get your tooth knocked out?
3 years ago.
3 what?
3.5 years ago.
That's awesome, dude. Is it like a rite of passage that you have to lose a tooth in order to play hockey?
No, I mean,
Just the good players?
just a good one.
All right, so here's what we're gonna do today. We're going to hit the puck and record it with a Phantom, which I have set up over there, and then we're gonna see exactly what's happening. I've heard that you don't actually hit the puck first, but I wanna look at the dynamics of how that happens. But first, let's look at your stick here. What kind of stick is that? Is it a wooden stick?
No, it's a one-piece composite.
Yeah?
Graphite. Mine's an 85 flex. I like mine a little whippier.
Whippier is
Yeah.
85. I love that word.
Yeah, well.
Can you say that as much as possible during this video?
Yeah, I can say it. It's a little more whip to it. You can get a stiffer one for the bigger guys.
I don't understand how you can hit that hard. That's crazy. I respect goalies a lot more now. Okay, let's get the Phantom. Whoa, all right, bring it. Okay, so we got the close-up shot. Now what we're gonna do is we're gonna transition to a wide shot. We're gonna keep the Phantom at 3,200 frames per second, but the goal here, the data we're looking for, is we're gonna try to preload that stick and get the entire flex, or the deformation of the stick, while he goes in for the slap shot.
The slap shot is the fastest shot in hockey. So what's the advantage of having a flexible stick? Let's check out the high speed. The player stores potential energy in the stick by striking the ice before he hits the puck. Now this seems like it would waste energy and slow down his shot, but it actually does the opposite. By gradually releasing that potential energy stored up in the stick like a slingshot, the player can make the puck go even faster than he can swing the stick. Look at the overflex here as the stick outruns the player's hands. This means that a good slap shot is all about timing, and not just the timing about where you're going to hit the ice, but also knowing how long it takes that stored up energy to whip out of your stick.
So to understand the flexibility of a hockey stick, we're here with my friend, Dr. Jeff Evans. We are friends, correct? Can I say that?
We are friends.
We are friends. I once tried to convince him to shoot a coyote in his pasture because I thought, no, it wasn't a coyote.
We thought it was a coyote. He thought it was a coyote, but it was a donkey.
It was a donkey. You break things, right?
We do. We break things by pushing, pulling, twisting, fatigue. We wear them out, we break them.
Okay, some bonus footage. We're going to crush a hockey puck here. Check it out. 80,000 pounds on a hockey puck. One interesting thing I discovered while doing this is hockey players often have no idea what the flex number on their stick means. If you support a stick on both sides here and you hang weights right in the center, that flex number that's on every single hockey stick is an indication for how much weight it takes to deflect a hockey stick 1 inch. The problem is often manufacturers don't do it correctly, so we have all these sticks from different manufacturers, and Dr. Evans is going to take the data as I apply weight to the stick, and we're going to measure the actual flex number against the claimed flex number.
We hung calibrated weights from 4 different sticks, each with a different flex number. Then we recorded the deflection values for each stick and generated a curve representing its stiffness. The flex value is the weight in pounds required to deflect the stick 1 inch. The numbers we measured, however, were much lower than the manufacturer's numbers, but this is probably because the sticks were used and they lost their stiffness over time. Check it out though, real science. Let's take a closer look though. A beam deflection equation can be used to model a hockey stick's flex. This force represents the pivot hand, and this force represents the stick hitting the ice. The maximum displacement happens right here in the middle where the player's hand pushes on the stick. In engineering, we use 2 types of diagrams called shear and moment diagrams to understand the stresses on the inside of a beam. So if our hockey player is strong enough to actually break a stick while doing a slap shot, according to science, where exactly along the stick is it going to break?
So where do you think it broke relative to where your hand was? Huh?
Probably in it.
Like you think it was in your hand when it broke?
Oh yeah. Yeah.
All right, let's make sure I got it on slow-mo.
Did you see that? There were 2 types of loading that added up to break the stick. First, he flexed it on the ice, but it wasn't until he tried to actually accelerate the puck that it kicked it up over its maximum stress limit and actually broke the stick. That is awesome.
So thanks for sticking with me as I try to explain a sport I don't truly understand. If you'd like to help Smarter every day and help me do crazy stuff like this, you can support the sponsor, which is audible.com. Go to audible.com/smarter. You can get a free audiobook. They've got thousands to choose from. Get whatever you want. You can do a free trial, free book, free trial. You can download it and listen to it, and if you don't like it, you can return it and get another one. It's a pretty good deal. Anyway, I used it long before they asked to sponsor Smarter every day, so I'm more than happy to suggest it to you. Audible.com/smarter. I get credit for you checking out Audible, and it helps Smarter every day move forward and do more crazy stuff. Anyway, I'm Destin. You get smarter every day. Thank you very much. Have a good one. Before and after.
It was a smashing good time.
You want more whippiness or more stiffiness?
All in preference. It's for science. I need a new stick.
Probably probably the most famous transformation of energy question is the roller coaster. And we get all sorts of different questions regarding roller coasters because they transfer energy from potential to kinetic to potential to kinetic back and forth as you go up and down the hills. So part A says, looking at this roller coaster with a mass of 255 kilograms at the top of an 18-meter hill, if the coaster just barely makes it over the first hill, so we're imagining that it came up from behind the hill, just barely gets to the top, meaning we're assuming V initial is essentially 0. It's so small, the coaster is still moving, but we can kind of ignore that amount that it's moving. And we're going to ignore friction. How fast will it be going at B, which is essentially at the bottom of the hill? So we don't really care that it went up again and came back down to get to B. We just want to know how fast it is going at B. So again, start out with this same equation every single time. PEI plus KEI equals PEF plus KEF, and let's see if we can eliminate any of these terms based on this situation. So at the top of the hill, we definitely have height, so we're going to have a PEI. So let's just rewrite that as MGHI. But we're told that V initial is 0. Essentially, it stops at the top of the hill. So we're going to eliminate the KEI from our equation. When we get to the part where letter B is, we are at ground level. So I don't have a height anymore. H final is 0. So I'm going to eliminate this PEF. But we are still going to be moving because that's actually asking what the question's asking for, how fast, what's my V final. So I'm going to rewrite this as 1/2 mv final squared. So this should look pretty familiar to you. Why don't you pause your video now and see if you can solve this one on your own, solve for V final, then plug in your information and see how it goes. So when you do your algebra to rearrange things, your V final ends up being the square root of 2GH initial. And this is going to be true pretty much every time all our potential energy turns into kinetic energy. And then you plug in your numbers and plug it into your calculator to get 18.8 meters per second. Part B then asks, suppose the roller coaster has an initial speed of 22 meters per second at A. How fast will it be traveling at B? Still ignoring friction. So instead of saying V initial is 0, now in part B, we're saying we have a V initial. V initial is going to be 22 meters per second. This is only for part B. Part A, we had V initial equals 0. So that's, again, going to change our equation just a little bit. So again, we're always starting out with this equation, but now that we have a V initial, we can't delete this KEI. We still can delete the PEF because my H final is still equal to 0, but our KEI we can't get rid of because our V initial is no longer 0. So plug in again your information or your equation. So PEI is MGHI, KEI is 1/2 MVI squared, and that's equal to 1/2 MVF squared. Now this one isn't any more tricky to rearrange. We're still looking for how fast will it be traveling, so we're still trying to get VF at B. And in order to rearrange this, we're going to multiply both sides by 2. If you want to distribute it, you can, or you can just leave it the way it is. And then we're going to divide out M, and because M is involved in every single term, we can actually eliminate it from the equation completely. So these cancel, those cancel, and I'm left with the square root of both sides. So VF equals the square root of 2 times GHI plus 1/2 VI squared. And at that point, you just got to plug in your information. So 2 times 9.8 times H initial was 18 plus 1/2 VI now is 22 squared. Make sure you get your parentheses in the right place when you plug that into your calculator, and you should be golden. So when I plug that all into my calculator, be careful of your parentheses, etc., you should get a final velocity at B now of 28.9 meters per second. 28.9 meters per second. So it is going a fair amount faster than initially expected, but notice that it's not just going 22 meters per second faster. If I went 18 plus 22, it would be a whole lot bigger than 28.9 meters per second. So don't just assume that you can take this initial speed and add it to what you already had. All right, on to part C. C says, suppose the roller coaster in part B, that means in this one that we just did, was actually only traveling at 25 meters per second at the bottom. How much energy was lost to heat? So now we've got this original equation, but we've got also this heat term coming in, and that's actually what we're trying to solve for, is the heat. And we've got now this as my V final at the bottom of the ramp. So instead of going the 28.9 that I would expect, it's only going 25 meters per second. How much was lost to heat? So let's see where we're at. We still can eliminate this PEF because we're still ending up at ground level, but everything else is going to stay there. So this is still mgh initial plus 1/2 mv initial squared is equal to 1/2 mv final squared plus heat. In order to get heat by itself, I'm going to subtract this 1/2 mv final squared to the other side. So heat is going to be then mghi plus 1/2 mvi squared minus 1/2 mvf squared. Notice that this is one of the cases where your mass does not cancel out, so I might have to go back to the original question and double check what mass was equal to. And at this point, we're just going to plug in my information. So going back up to see, mass was 255 kilos. So that's going to be plugged in every single m. So 255 times 9.8 times h initial was 18 plus 1/2 255. This was my 22 meters per second that I started with, squared, minus 1/2 times 255 times 25. This is my V final now, squared. Plug that all into your calculator and see how it goes. And the number I'm getting coming out of there is 27,000 plus 4.5. Round that to 2 sig figs would be 27,000. To get 3 sig figs, you'd have to write it as a scientific notation. But this 2 sig figs is good enough. So this is going to be 27,000 joules is lost to heat by changing my velocity just by that 3.9 meters per second. Okie dokie, let's keep going. Example number 4. A 75 kilogram cart and rider starts from rest on a 20 meter high ramp. My velocity at the bottom is 16 meters per second. That's a typo, give me a second. So the speed at the bottom of the ramp is 16 meters per second. How much energy was lost to heat? So this is the same kind of question as we just answered. Why don't you pause your video, try this on your own, see if you can set it up, solve it, see how you did. Then we'll go through it together. All right, here we go. So we're starting out with this same equation, that we always start with. PEI plus KEI equals PF plus KF. And in this case, we're looking for energy lost to heat, so we need this heat term in there. Now at the top, we definitely have potential energy because we've got a height. This is our height initial. But we are starting from rest, so that's going to mean our KEI is eliminated. At the bottom, we hit the ground. We no longer have a height, so my PEF is gone, but I am moving, so I have a KEF. PEI is mgh initial. KEF is 1/2 mv final squared, and I've got heat coming along. And to solve for heat, again, I'm going to subtract this term to the other side, so I've got heat is mgh initial minus 1/2 mv final squared. Plug in the information that you have. M is 75, G is always 9.8. H initial is this 20 meters. For this part of the question, the 60 meters is irrelevant because our potential energy determined by only height, not by the distance that he goes, minus 1/2 times the mass, 75, times the V final, 16 squared. And when I plug all that into my calculator, I get that he loses approximately 5,100 joules to heat. If you need time to write that down, you might want to pause your video because we're going to go on to part B. Part B says, what was the average force of friction? So friction is what did this work to turn the energy into heat. So if I'm thinking in terms of work equals force times distance, and I'm trying to find force, I'm going to divide both sides by d, so force equals work over distance. And the force was exerted over the distance of 60 meters. This is where the 60 meters becomes important. So friction did 5,100 joules of work to produce heat over 60 meters of distance. So this is going to be the 5,100 joules divided by 60 meters. Plug that into your calculator. And that tells me the average force is 85 newtons. So again, work equals force times distance. When we're talking about heat, that's the work done by friction. So this is force of friction times the distance that the object traveled, not its height. A few more examples to do before we get to the end, but actually before we do our next example, you're going to watch another video clip. Rube Goldberg machines are kind of a series of events that trigger another event in order to get a job done in a way more elaborate way than you really need. But it's kind of fun to watch things trigger other things, so watch for the transformations of energy in this video called Sprice.
My name is Steve Price. My stage name is Sprice. I'm 19 years old and I'm from Canton, Michigan, and I build Rube Goldberg machines. If anything goes wrong, it would be my performance part of it because I'm not that energetic, but I can build things and it's really cool, so
hey, you're energetic.
They should watch it. A Rube Goldberg machine is basically a huge chain reaction with the goal of finishing some kind of simple task. Half the time I tell people what I do, they have no idea what I'm talking about.
All right, what you gonna do today, Sprice?
I have a Rube Goldberg machine set up in the lobby. I don't know exactly what I'm gonna build yet, because usually when I build, sorry, my voice cracked. My act is all about chain reactions, and I hope the final reaction is the judges sending me to Vegas.
Have fun.
All right, thanks.
Go get him. The what? Bird machine?
Hello.
Hi.
Hi.
Hi, what's your name?
My name's Bryce.
What brings you to America's Got Talent?
I build Rube Goldberg machines.
Oh, no kidding.
I love those.
That's very cool.
You actually know what it is. I'm pretty surprised.
Absolutely, I do.
I don't know what it is.
You know when a ball hits something and then knocks that, and then that does something, and then that does something,
Exactly.
and it hits you in the head.
So this has got to be a big operation, right?
Yeah.
All right.
I've been setting up my act in the lobby the past 3 days, so when you guys are ready, I'd love to come show you.
Good luck.
Let's do it.
All right,
All right.
thank you.
All right, Sprice. We brought the entire audience out in the lobby, judges included. How do we start it? Where's the on switch?
The very first domino is right at the edge of this table, and I'd like to ask you to do the honors of knocking it down.
Me?
Yep.
Audience, 5.
Yep.
Holy moly. Oh, this is the greatest.
Supposed to be having
This is the risky part. Yep.
It's the risky part.
Oh, no. It's gonna...
Spin.
You're gonna hit it?
Genius.
Go on out there, Sprice. Go get him.
My man Sprice, I love this kind of thing. The idea that you sit in a room and you create this, your mind's got to be something else. I love it, and congratulations on that working out. That was quite an accomplishment.
Thank you.
I liked it. Heidi.
I loved your act a lot because it was really simple, actually. Anyone can really do it if they got the brains like you do and the talent to do it. I absolutely loved it.
Mel B, do you love this?
You know what? Yeah, I do. If it's a minuscule out, any bits of those material, the whole act is kaput. I found it very unique and creative. So thank you.
Howie, I'm guessing you really liked it.
I love this kind of thing. If I can be a little critical, I would tell you, number one, lay off the caffeine and bring it down a little bit because the excitement is killing me.
Sorry about that.
Are you excited to be here?
Of course.
I can tell. Look at you.
Mel B, what's your vote?
Oh, it's a definite yes from me. I want to see more.
Heidi Klum.
I want to know what you're going to come up with next. Definite yes for me, too.
Howie Mandel.
You know, on this show this year, 3 yeses mean you're going to Vegas. And you know what? You just got 3 yeses.
We'll see you in Las Vegas at the yes. Thank you. As time goes on, will he dress a little better?
He's just no energy. But you know what? I think you got to be that
He's
focused.
cerebral.
Because all he's doing is just setting
Little
things up
things,
out.
yeah.
If you're hyper at all, I wouldn't be able to do that.
You're going through.
Yep.
Still no excitement, huh? That's as much as we can get.
I'm not going to express it.
You can't turn it up a little bit, get a jump or something?
Now that you've had a bit of fun, here's our second last example. Example number 5. A bouncing ball is another great example of the law of conservation of energy. So at the top of the bounce, so it comes down, hits the ground, comes back up, hits the ground, comes back up, hits the ground. At the top of any of these bounces, what type of energy does the ball have? Well, at the top of these bounces, it comes to a stop, hits a maximum height, so it's not going to have kinetic energy, but it does have a height above the ground, so it's going to have potential energy. As the ball hits the ground, what type of energy does the ball have? Well, when it hits the ground, its height is going to be 0, so it doesn't have potential energy. It's all kinetic energy. The ball loses height on each bounce. Does this violate the law of conservation of energy? In this case, the answer is no, it doesn't. It's losing energy due to heat, because of air resistance, because of friction when the ball is compressed. There's a sound when the ball hits the floor. So no, it doesn't violate the law of conservation of energy because energy is transformed into heat, into sound, through air resistance, through compression of the ball. So there's your written explanation. You may need to pause your video if you want to write it down. Part D, is it possible for a ball to bounce higher than it was originally dropped? Well, unless there's an extra force pushing on it somewhere, pulling it, maybe it's a magnetic ball being pulled up, the answer to that would be no, because we're not putting energy into the system, so that maximum PE would be what it started with. And again, there's your written explanation if you need one, or write it in your own words. So we're going to take one more pause for another fun video, the stacked ball drop. And again, think about all your transformations of energy that you see as you watch.
Check out how high these different balls bounce. The basketball, the super bouncy ball, and the golf ball. Now I'm gonna try the golf ball on top of the bouncy ball, on top of the basketball. And then I'm gonna explain how it's related to a supernova. Did you see that? Probably not. So here it is again. The golf ball bounced to 28 feet. We dropped it from about 3.5 feet, so it went up 800% of its dropped height. In fact, if you consider that by itself, the golf ball bounces about 70% of its dropped height. It went as high as if it had fallen from 40 feet up. That is awesome. So how can we get the golf ball to bounce up with that much energy? Let's simplify it to these two balls. When you drop them individually, each ball starts out with some potential energy from the height of the drop. As the balls hit the ground, some energy goes into heating up the ground and some goes into heating the ball. Because that energy left the ball system, you can't get back up to the same height. But when you combine them, the tennis ball goes higher than its dropped height. Way higher. Where does it get the extra energy? As the basketball bounces, it compresses, storing elastic potential energy. As it releases, it springboards the tennis ball upward just at the right moment. This is like the double bounce on a trampoline when you jump right before someone else. You prepare the elastic of the trampoline by stretching it and storing energy, which can then bounce the jumper even higher. In the same way, the basketball stores energy in its compression and is able to push the tennis ball. But just like the double bounce preparer, the basketball can't go as high. You can see that here. It bounces even less when 3 balls are dropped together. Also, during that transfer of energy, some momentum transfers from the basketball to the tennis ball. And since the basketball starts with way more momentum because of its larger mass, the tennis ball's velocity increases by a lot. And it flies up, and away. Now back to the triple super ball bounce. Now you get the energy from the basketball's bounce being transferred into the bounce of the super bouncy ball, which is then transferred to the golf ball's bounce. You put the same amount of energy or momentum from 2 more massive objects into a smaller object, and it will go much faster. Epic! Just like the explosions of a supernova, which may seem unrelated, but what we just did is analogous to the process that occurs during the explosion of a supernova. Just like our more massive basketball transfers momentum to the smaller balls, energy from the dense core of the supernova is transferred in a shock wave that moves through the star to the less dense layers and accelerates them outward at a super high velocity. More massive or denser layers in the core of the supernova begin to collapse when fusion stops there. The collapse is halted when the neutrons in the core actually touch, sort of. This causes the implosion to rebound and bounce outward. You end up with a dense core left behind and these wild outer shells of star exploding outward. Pretty cool. And of course, if you try this at home, which you should, you have to make sure the balls are perfectly vertically aligned because any off-centeredness gets amplified by the 2 points of contact, which is why we sadly couldn't get the quadruple tower of balls to work. But if you put a little ring of hot glue or something similar on the balls, it helps to balance them. Happy physicsing!
Last question is not really a law of conservation of energy question so much as it is thinking through kinetic energy. So it says, a golfer wishes to hit his drives further by increasing the kinetic energy of the golf club when it strikes the ball. Which would have the greater effect on the energy transferred to the ball by the driver? Doubling the mass of the club head or doubling the speed of the club head? So again, we know kinetic energy is equal to 1/2 mv squared. Doubling the mass of the club is going to double the kinetic energy. So twice as much mass, twice as much kinetic energy. But we know that doubling the speed of the club, twice as much v, is going to square that, is going to be 4 times as much energy. So which would have the greater effect on energy transferred to the ball by the driver? Doubling the speed because it's squared in the equation. All right, that's it for this lesson. Now you get to practice transformation of energy questions. Good luck!